So we continue today's morning program with the last installment of Martin Harris mini course. Martin, do you hear us?
Yes.
Okay, perfect. So I give you the floor.
Okay, thanks a lot. So remember last time where we ended yesterday's lecture with writing down formally this kind of stochastic gradient flow for the Yang-Mills equation. So here, this term here, you should think of it as minus the gradient of the Yang-Mills action. And well, so I mentioned to you this idea of Parisian rule to say that if you wanted to build this Yang-Mills measure, which is formally e to the minus the action, then one way of doing this would be to build, this stochastic gradient flow, and then to exhibit an invariant measure for it. And formally, at least if by analogy with what happens in the finite dimensional case, that invariant measure should be e to the minus s of a. Now, remember, also, I don't remember if I mentioned it yesterday or the day before, but one of the problems, right, in Yang-Mills is that because of gauge invariance, you have these infinite dimensional gauge orbits on which the action is constant. And, well, we already mentioned that this would clearly be a problem if you try to build the Yang-Mills measure as a measure on a space of connections. And we see a kind of reflection of this problem here, which is that, well, since this here is the gradient of S of A, formally, well, what this suggests is that this vector field, if you want, at every point sort of points in a direction that's orthogonal, right? So that would be minus gradient S of A. So, well, because it's a gradient and S is constant on these sets, well, these gauge orbits are basically part of the level sets of S, and so the gradient should be orthogonal to that. On the other hand, the noise here acts, in a kind of uniform way in all directions, right? So the covariance of the noise is the identity, so it acts sort of in the same way in all directions. And again, what this suggests is that if you can somehow give a meaning to this equation, then, well, it would just sort of diffuse along these gauge orbits in a kind of completely uniform way, which means that, again, its invariant measure should be something like Lebesgue measure on these gauge orbits. And, well, we've already seen that that's a problem. So now there's a trick that one can use to, so of course there was one trick was to simply collapse all of these gauge orbits into one, but then again we're back in the situation that that makes the state space sort of nonlinear, difficult to describe. It would be even more difficult to write down some kind of SPDE here. So the trick that was found by actually de Turck in the context of the study of the Ricci flow, which has a similar problem, and then it was adapted by Donaldson for the study of the Yang-Mills heat flow. So the trick is to say, well, why don't I just perturb this equation? I add an extra term. So here I add some extra term, and I do this in such a way that the extra term points in the direction tangent to the gauge orbits at every point. Okay, so if I do that, at least formally, well, of course I change the equation, but as far as the evolution on the space of gauge orbits is concerned, I shouldn't change anything, right? Because we really want to identify all these gauge orbits with a point, and therefore moving sort of along the gauge orbit by the time you perform this identification has absolutely no effect, right? In particular, since one can actually check well, it's a somewhat easy calculation, but if you, at least formally, right, if you take this equation here, you start it from A, or you start it from, you know, another point, AG here on the same gauge orbit, if you look at the two solutions, they should be equivalent in law, in the sense that if I take the solution to this equation starting from here, and then I just apply the gauge transformation to it to move it to here, then in law that's the same as just starting the solution to that equation from here. And that can be seen easily by just conjugating with G the whole equation, and this term here is basically gauge invariant, so conjugation with G is the same as simply turning A into AG in this term. And for the noise, you end up with a noise that's conjugated with G, but conjugation with G is an orthogonal transformation of the noise, so it doesn't change its law. Okay, so because of that, this equation, at least formally, is sort of invariant in law under the action of the gauge group. Okay. So what this tells you is that if you add some additional drift to the right-hand side of the equation, as long as this drift always points in the direction of the gauge orbits, it effectively doesn't have any effect on the dynamic on the space of gauge orbits. Okay, so of course all these considerations are completely formal because we haven't even given a meaning to this equation. And now, well, so let's try to see what's the form of these vector fields that we're able to add. Right, so if you want, what does the tangent space to the gauge orbits looks like? Well, so I take one of these gauge orbits, right, AG, so let me call that OA. So that's the orbit that passes through the connection A. And then one way of figuring out what the tangent space is I just take a time-dependent gauge transformation, right, where the GT is in the curly G, right, so GT is still a function from, say, RT into the Lie algebra. So I take a time-dependent gauge transformation and I apply it to A, right, so I look at A GT. So it basically means I look at a curve in this gauge orbit, and then I just compute the derivative. And if you do the calculation, so that's a simple exercise, just comes from the form of the action of the gauge group on the space of connections. What you find is that you get here minus the covariant derivative with respect to AGT of the time derivative of G. Now this is arbitrary because I just take here an arbitrary G, and so that tells me that the tangent space at A of OA is actually all the elements of the form DAH with H function from RD into the Lie algebra. Oh, sorry, this was rubbish here, so it's not in the Lie, here it's in the Lie group. Okay, so that tells me what the tangent space looks like. And so that tells me that here I can add any term which is of the form dA of H. And H is, well, if I want to make it autonomous, H, I can just take any function of A. And so then the idea by Donaldson is to take H equal to minus D star A. And why is that a good idea? Because now if you look at the equation, oops, why is that? Okay, now it works again. So the equation looked like this. So I add this term, which is a dA d star A, and then there's the noise. Now, what does this look like? Well, remember, FA essentially looked like the exterior derivative of A, right? FA was dA plus an extra bracket. And then these covariant derivatives also basically look like exterior derivatives. So the covariant derivative is also exterior derivative and then plus some bracket term. And so the first term here basically looks like d star d, A. And the second term looks like dd star A. And then there are lower order terms. And then there's the noise term.
Martin?
Yeah, is there a question?
Yeah, I have a naive question. Is it like similar to evolution in some particular gauge?
Right. So in some sense, so what people call this in some sense time-dependent gauge fixing. So it's a little bit like fixing the gauge, except that you don't fix a representative, right? Yeah, but you fix somehow the evolution along the gauge orbits.
So does it mean that you modified effectively you modified the Yang-Mills action to make it right? There are those those mechanisms where you add some term which make now the propagator more or less non-degenerate. Is it similar to that?
No. So here you don't touch the action. I mean, you change the form of the equation, right? So it's not of gradient type anymore, right? So this is not of the form gradient of a modified action.
Oh, okay, thanks.
So you just add a term. So you don't care about whether this term is of gradient type. I suppose it would be, right, you can kind of think of it like that, right? So it is a little bit as if you added sort of like a quadratic term to the action that kind of pushes you this way around, but you don't actually care about this being of gradient type. The only thing that you care about is that that you have a guarantee that the additional term pushes you along the gauge orbits. And so it doesn't change the dynamic.
Okay, thank you.
Right, and so now this here is just a Laplacian of A, right? Whereas if you didn't have this additional term, right, then you would only have this sort of 1/2 of the Laplacian if you want. And well, if you do the calculation, this term by itself is not actually an elliptic operator, right? So it's something like Laplacian of A, and then there are some mixed second derivatives of A that show up, and they show up in such a way that the operator is not elliptic. Whereas if you add these terms, then you get just a regular Laplacian. And so what this tells you is that, it shows that you have a much better chance, if you want, of being able to study this equation from a sort of rigorous mathematical point of view than you do for studying this equation, right? Because this equation is not elliptic, not parabolic, so it doesn't actually have good regularizing properties or anything. This noise is extremely singular. And so without this term, it would be basically hopeless to study this equation for basically, for the reason that we already mentioned several times, is that it kind of wants to be Lebesgue measure in the direction of the gauge orbits, which doesn't exist. Right? Whereas now with this additional term that kind of pushes you back, it makes somehow the equation much more coercive, kind of pushes you back towards compact regions. And so you have a much better chance of being able to give a meaning to this equation. Okay? And well, the hope, right? So what you would hope is that you would still have the property that if you start from two different initial conditions on the same gauge orbit, and you look at the law of the solution. So now this time it's no longer going to be the case that, you know, that the solution here is just the same as the solution here transported over there by conjugation with G, not even in law. But what you can hope is that you still keep the property that if you start the solutions from two different initial conditions on the same gauge orbit, that if you look at the law of the solution and you project onto the equivalence classes, right, so you project down onto the space of gauge orbits, that then they are the same in law, right? So that's the property that you would want, which then tells you that, you know, this would actually give you a Markov process on the space of gauge orbits. So now what's the wish list, right? So the wish list is, well, so the first item, right? So if you now want to kind of push through this program, okay, from a, you know, in a mathematically rigorous way, what are the, you know, ingredients that you actually need? What are the objects that you need to construct? So the first thing you need is actually a state space, right? So you need to find a state space of connections. Let me call it X, curly X, which is sort of large enough to accommodate the solutions to that equation. So let me call it stochastic Yang-Mills. And, well, if you actually, well, for those of you who are somewhat familiar with these equations, if you ignore this, right, so the equation is just a heat equation plus noise. Heat equation plus noise, after basically any fixed amount of time, the solution looks like a free field. Okay. Well, that's basically because this would be the gradient flow for just the free field action, right? So the e to the minus integral gradient a square. And the free field, you know that as soon as you're in dimension 2 or higher, it doesn't live on functions, but it lives on distributions. And the higher the dimension, the more singular the distributions that it lives on. Right? So here, this forces X to contain distributions. Now, you want X, on the other hand, X should be small enough so that Wilson loop observables make sense. Right? So you would want to have some physical observables. The natural ones are the Wilson loops. So you would want to, you know, X to somehow contain, right? If X is too large, if it contains sort of arbitrary distributions, for example, there's no chance of being able to define Wilson loops in a meaningful way because distributions, right? The Wilson loop, the definition involved, well, you know, taking a loop on your base space and then following the connection along the loop. That's certainly the least that you would need for that is to be able to actually restrict your connection to a loop, to the one-dimensional subset of your underlying space. And in general, you can't, right? I mean, an arbitrary distribution cannot be restricted to a line. Yeah. And so here you want to be able to, for example, restrict elements of X to lines, or smooth enough lines, for example. Right? So then you want to have an equivalence relation on X, which is interpreted as, well, A equivalent to AG for G in curly G. And then again, now you have to be a little bit more precise about what you actually mean by curly G, because so far I just said, well, curly G are functions from RD into the structure group. But now you have to ask yourself, what sort of functions do you take? Of course, you can always take smooth functions. So if A is an arbitrary distribution, this operation still makes sense for smooth functions. But then if you only take smooth functions, then this equivalence relation here is going to have really, really bad properties, right? So it will be, it would be a little bit similar to looking at the equivalence relation, say, on L2, which is given by two functions are equivalent if their difference is a continuous function, right? So, or a smooth function, right? So this is a really, really badly behaved equivalence relation on L2. So if you sort of think about it a little bit and you try to think about what the quotient space for that equivalence relation would look like, well, you find out that you can't really describe that quotient space, and actually it's not even a Borel space, so it doesn't have any good measurable structure or anything, so it's an absolutely horrible space for analysis and probability. And so you cannot just define the equivalence relation like that, because then the space of gauge orbits would be an absolutely horrible space, right? And so you would want to do this in such a way that X quotiented by this is sort of nice in some sense, right? And then what you want is, well, you would want to construct a Markov process on X that can be interpreted as solution to this stochastic Yang-Mills equation. Right? And then you would want to have the property that pi x is still Markov, where pi is the projection that goes from x to x modulo this equivalence relation. And then, even better, you would want to know that pi x has a unique invariant measure on the space of gauge orbits. And then finally, in 2D, identify the measure with the known law of the Wilson loops. Right? So in 2D, we know the joint law of the Wilson loop observables, and so if you have a measure on that space, and that space is nice enough so that Wilson loop observables make sense, then that gives you a joint law as well, and you would want these to be the same. Okay, so that would be sort of full wish list of the sort of things that you want. And so now let me tell you how far we are sort of down that wish list. So first point is fine. So we have some results in 2 dimensions, some results in 3 dimensions, and the results in 2 dimensions are somehow more complete than the results in 3 dimensions. So the first point is fine in either of the two. The second one is fine in 2D, and it's sort of almost fine in 3D, in the sense that in 3D you don't actually expect Wilson loop observables to make sense, because even the free field just cannot be restricted to lines in 3 dimensions. And so the next best thing that you can do is have some notion of smoothened Wilson loop observable. So in 3D, we do have a notion of smoothened Wilson loop observable, which makes sense. Then the third point, we have a way of doing it, different ways of doing it in 2D and in 3D. And what we mean by nice, in sense, in 2D, in our construction, nice is really nice, in the sense that the quotient space, you can turn it into a complete separable metric space. So it's basically the nicest kind of space, topological space that you can think of. And in 3D, we can still perform a similar sort of construction, but the space of gauge orbits is much less nice. Okay, so it's still a topological space, it's Hausdorff, but it doesn't, for example, we don't know whether it's metrizable. It is separable though, at least. Then in both 2 and 3 dimensions, we can give a meaning to that equation. So we can construct a Markov process on that space, which can be naturally interpreted as solution to the stochastic Yang-Mills equation. And we can do it in both cases, we can do it in such a way that the projection is still Markov. Right? And then regarding the invariant measure, what we know in both 2 and 3D is that we have at most one invariant measure, but we don't actually know existence. Right? So it's one of these somewhat rare cases where it's somewhat easier to prove uniqueness than it is to prove existence. So we know that if it exists, it's unique, but we don't know that it exists actually. And the last point, we don't have that. So that's about the status of things.
Martin?
Yes.
Sorry, may I ask a somewhat provocative question? So you mentioned 2 and 3D. What about 4D?
4D is really problematic, yeah. So in 4D, we know absolutely nothing.
Even the first items? No, nothing?
Even the first items.
We know it doesn't work, or we just don't know how to make it work?
We don't know. Well, okay, so there is, for example, there is a very recent work by Kao and Chatterjee, which is not yet published, but there are some videos online, where they give a candidate for such a state space in 4D. But it's an extremely weak space. So in some sense, it is a little bit like a sort of gauge invariant way of saying just the space of all distributions. So, for example, in the case in which the gauge group is abelian, that space would just be, actually, it would even be larger than the space of all distributions. It would be like almost more like a space of generalized functions a la Colombo. So it's an extremely large space which they are considering, and so it's definitely way too large for any of the other, for example, for the second point or anything. In 4D, sort of the reason why everything breaks down in 4D is that dimension 4 is the one which is really critical for this equation, in the sense that what I wrote as lower order terms here are not lower order anymore. I mean, in the sense that in terms of scaling, so these lower order terms, they basically look like one term which is bilinear in A and its derivative, and one term which is trilinear in A. And if you, in 4D, if you want the scaling dimension of A would be -1, and so A times derivative is of dimension -2 if you want, and A square is also of dimension -2, and so all three terms here scale in the same way. And so there's absolutely no theory that allows us to do anything there in the stochastic case.
Okay, thank you.
Yeah. Okay, so now what I want to, so again, so both of these, so the 2D work is online on arXiv, the 3D work is not yet on arXiv, and both of these works are joined with the same set of co-authors that I mentioned last time. So A.J. Chandra, Ilya Shevorev, and Hao Shen. So, okay, so since I have about not much time, 20 minutes. So I want to then just discuss sort of that point here, and in particular, this part here, right? So like, how do you guarantee that sort of thing? So, construction of the process. So here I'm just going to now use like brutal black box results, and I'm going to just, you know, ask me to trust me. So I'm not going to go into details of the construction, because that would be that would take way too much time. But the idea is that, well, so first in terms of scaling, remember, so the equation that we're looking at, so I mentioned that it basically looks like this, where here the products should just be interpreted as, you know, suitable bilinear and trilinear forms, so that the equation is like that, right? And then you have this white noise here. So what you want to do is you want to somehow regularize this equation and pass to the limit, right? So that's basically the standard way of going about things. So what you would do is you would replace this noise by some kind of smoothened out noise. So essentially replace all the delta functions and the correlations of the noise by, you know, some epsilon approximations of delta functions. And then you want to pass to the limit. And here you have there's a general theorem. So if I basically write, so for example, write, say U epsilon of, and actually it's going to be convenient here to allow me to change the strength of the noise. Okay, so I'll put a sigma here in front of the noise, and I'm going to just call the whole right-hand side here somehow F sigma. And so now let me write U epsilon of F sigma for the solution to the modified equation, right? And then so there's a general theorem which says that there exists finitely many counterterms. And this is, again, this works in dimensions strictly less than 4 here, okay, because it requires, again, in terms of scaling dimension, it requires these two terms to scale better than that one. So that again goes with Anton's question. So here there are finitely many counterterms, let me call them whatever, G tau, such that and constants C epsilon tau, such that if I look at the solution to a modified equation, so I look at F sigma plus sum over tau of C epsilon tau G tau, so this converges to some limit, which I call U of F sigma. So this is by definition, if you want. That's the definition of U. So that this limit exists, and the limit is independent of how you modify the noise. So here, these counter terms, they are of lower order, and so that means that in this case, well, essentially the counter terms are obtained by looking at the monomials that show up on the right-hand side and removing some factors. So if I remove some factors here, I can get, well, there's a dA, so I could remove the A guy, I get a dA. I could remove the dA guy, so I get an A. And here I could remove one of the A's, so I get an A square. And I just could remove, if you want, all of them, and that gives me constant, right? So there are essentially 4 types of counter terms that could appear, right? And the general theorem tells you that, well, if you modify the equation here by adding these counter terms with some constants in front of them, and these constants might diverge, then you converge to a limit. And of course, that's not really what we want, right? Because we wanted to give a meaning to this specific equation. We didn't want to modify the equation, right? Now, for symmetry reason, you can actually rule out a bunch of these terms, because if you look at this equation here, you find that if you replace, right, if you look at the substitution x goes to minus x and simultaneously a goes to minus a, then every term in the equation changes sign, right? So this guy changes sign because a changes sign. This guy changes sign because a changes sign. This one also, because you have 2 a's, they change sign, so that cancels each other out, but you have a derivative, and that also changes sign because of x going to minus x, and so on, right? So this equation is invariant under this substitution. And then there's a general principle that tells you that, therefore, the counter terms that show up should be the ones that are also invariant under this symmetry. And here you find that this one is the only one, right? This one, under this substitution, doesn't change sign because both sign changes cancel out. Same for that one, same for that one, right? So actually, all these counter terms are ruled out, so that's already a bit better, right? So now it already tells us that the only thing that could possibly mess our equation up is that there could be a counter term which is some kind of constant times A. Of course, when I mean constant here, it means constant, I mean, it could be a matrix, right? Because A is vector valued, right? It takes values into the algebra. So constant here really means a linear operator from the algebra to itself. So now, okay, so that's still not quite well, it looks like it's not quite what we want, right? Because even if we add, for example, if we add this term, well, first we're actually changing the equation, and then we're actually breaking gauge invariance, right? So this equation had this property that, at least formally, you can actually find out. So here, if you look at the solution at later time, so a at time t, you can kind of relate it to the solution starting at a different point, as long as you actually perform a time-dependent gauge transformation, right? So this is a formal calculation one can do. So one can actually figure out how the solution starting from different points on the gauge orbit should relate. This formal calculation relies on the equation being exactly that. Right? So if you add a term which is proportional to A, that formal calculation breaks. Okay. On the other hand, that formal calculation also relies on the covariance of the noise here precisely being the identity operator, right? The noise being right, not just in time, but also in space. And that's used because when you compare these two solutions, you really compare a guy driven by the original noise to a guy driven by the noise conjugated with G. But G is x-dependent, and so conjugation by an x-dependent function is an orthogonal transformation for white noise, but only for white noise. So if you somehow change the covariance of the noise, it's not an orthogonal transformation anymore, and so it's going to change the law. Okay? And so what we conclude from that is that, well, first here, when we mollify the noise, we actually break that gauge invariance. Right? So we break this property that the solutions starting from two different initial conditions are actually related to each other by a measure-preserving transformation. And so the hope is that actually, if you choose the constant in front of that A term just right, then, well, this might break the gauge invariance in a way that just cancels out the way we've broken it here. Okay? Now that's, of course, a priori, there's absolutely no reason for this to be the case, right? I mean, we sort of break it in two different ways that appear to be completely unrelated. One of them is by adding some sort of mass term to the equation. The other one is by changing the noise, coloring the noise. There are completely different ways of changing the equation. The claim is that it is possible to choose, right? So let me just, right here. So first, right, since we restrict ourselves to this term here, we're really considering, right? So now we consider ETA, Laplacian A plus ADA plus some sort of A cube, and this guy is gauge invariant. And then we have an epsilon dependent constant times A. And then we have this epsilon dependent noise. Okay, and this constant here, in general, C epsilon actually belongs to linear operators from the Lie algebra into itself. And so the claim, now first, this theorem tells us that it's possible to choose the C epsilon in such a way that this converges to a limit, okay? But it doesn't tell you that it's unique. And as a matter of fact, it has just no reason at all to be unique, because if one choice of C epsilon makes this converge to a limit, then just adding a finite number to that choice will also make this converge to a limit, right? So the changing C epsilon by a finite amount will just make this converge to a different limit, okay? So here in this theorem, you don't have any sort of uniqueness statement of what this limit is. And so by itself, this statement doesn't even quite construct one Markov process, but it constructs a whole family of Markov processes, and then we still need to pick the right one. And a priori, it breaks that property for all of them, right? And so now the claim, or the theorem, if you want, is that there exists actually a unique choice of C epsilons, and that choice is actually proportional to the proportional to the Casimir, which is the identity if the Lie group is simple. So there exists a unique choice of these C epsilons such that the A epsilons, so that's the A epsilons, converge to some limit A. And so that's not just, as one single guy, it's really convergence as somehow a flow, as a Markov process, so that these A epsilon converge to A, and a is gauge covariant, in the sense that I already tried to explain several times, right? So in the sense that if I start with two different initial conditions on the same gauge orbit, and I look at the two solutions, then they can be related by a random gauge transformation, for example. Okay. So that's one way of formulating this. And okay, so I think, okay, so unfortunately I don't have, I think I'm actually already at the end of the 45 minutes, right? So yeah, so I think actually showing that I wanted to show to give some idea of how to prove that. But I think even in the simpler case, that would probably take about 15 minutes, which would be too long. So the best is probably to just stop here and to take questions. And well, thanks a lot.
Right, thanks a lot for your mini course. Are there any questions, either in the room or online? Yeah, maybe in the meantime I can ask one more question. So Martin, this 2D and 3D, you're doing it on R2 and R3, right? So
no, we're actually doing it on the torus. We do it in finite volume.
Okay. Okay.
Yeah, sorry, I should have mentioned that.
More questions? If not, I can of course generate an arbitrary number of questions, but I think that's yeah. I have maybe one more, unless someone wants to ask a question. So Martin, you mentioned that in 2D you don't know yet whether it coincides with these whatever Migdal answers or so the answers that we know in 2D, and how far is it, kind of how difficult, or what are the abstractions? How far is it from knowing that the answers are the known answers in the literature?
Okay, so I think to some extent the obstructions are mainly technical and not really conceptual. So what you would want to do, right, is you want to take, so if you want to prove that, you would want to have some kind of discretization of which, you know, you have convergence to both of these processes simultaneously, right? And then they have to be the same, in some sense. And so the natural candidate for that is to do some kind of lattice gauge theory, right? So you would somehow just stick your gauge theory onto a two-dimensional lattice. And that one, for that, the Wilson loop observables, you know, are known to converge to the limit that we know in 2D. And so then you would want to actually put a dynamic on this lattice gauge theory, which makes it converge, you know, modulo the correct time-dependent gauge transformation, makes it converge to the same limit as that guy. And now, of course, if you just look at what that lattice gauge theory looks like, well, it mostly just sort of looks like a discretization to this equation, right? But, you know, with a whole bunch of epsilon, so now epsilon would be sort of the size of your lattice, right? So that would be epsilon somehow. So you have a different somehow epsilon regularization of that equation, and you want to show that the two epsilon regularizations give you the same limit. And in principle, we have the tools to do that sort of thing. The problem is just that that discrete version looks like a very messy regularization, right? So you end up with a whole bunch of somehow epsilon dependent terms, which you need to show, you know, either combine in such a way that they disappear, or just, you know, combine in such a way that they contribute to whatever you want to see on the right-hand side. And doing it sort of by hand is somewhat hopeless because you have sort of explicit formulas for the way these things converge to a limit, but these are essentially untractable. So you need to actually exploit like symmetry arguments and the fact that you have gauge invariants, and that gives you a lot of rigidity. So you can kind of exploit that rigidity. And in principle, we sort of know how to do that. But at the discrete level, there's just too many messy terms that show up. It's mostly technical. I mean, I don't think that there's really a real conceptual hurdles now.
Okay.
But it would be quite a lot of work.
Thanks a lot. Well, yeah, so the last chance we have over there. Oh. But that's probably, unfortunately, the last question in this session. Okay.
So thanks a lot for the nice lectures. Do you think the method will also be able to include coupling with fermions in perspective?
That's a good question. So of course, the stochastic quantization business works quite well for bosons, and we can couple this with bosons. So you can do Yang-Mills Higgs, and you know everything that I said is true also for Yang-Mills Higgs. Fermions are a different story because you don't have such a sort of nice, straightforward probabilistic interpretation. There is some recent work by Albeverio, Gubinelli, and other co-authors, which goes in the direction of somehow building a kind of stochastic quantization for fermions that is closer to the sort of things that probabilists are familiar with. And so, yeah, so there is some recent progress somehow in this direction, but we're still pretty far.
Okay, thank you very much.
All right, so thanks a lot, Martin. Let's give a very big applause to Martin for his mini-quiz. So thanks again, and we resume very shortly with the next mini-quiz.
Okay, thanks. See you.